Hey guys, wish you a very good evening. Glad you could join in, especially on a Friday evening. Hope you guys are doing well. Okay, nice. Oh, I'm lagging a bit. Let's do one thing. Okay, I see. Let's do one thing. I'll turn off my video for a while. If the connection is bad, okay, nice. Sumit has given me the this thing. Let's just give me 1 second. I'll see if I can. I'll try turning off my phone's Wi-Fi. That should do it. Hmm. So OTP is done. So I'm glad that my screen is readable. Is the lag still there? Is the lag still there for my voice and video? No, right? Okay. So guys, in case it turns out that there is some lag, I will turn off my video today. Like that seemed to fix the problem last time. So the moment, so actually I get a notification here if my connection is unstable. So the moment I spot that, I will turn off my video. So don't be shocked if suddenly the screen goes blank. So yeah. Okay, awesome. So we're going to study something interesting today, long short-term memory. We've finally come to the fun part of NLP. Basically, the most exciting results that we have gotten. Uh, the work that went towards those most exciting results started with RNNs, right? Today we're going to see how a slight change in the architecture of an RNN will help us actually solve a couple of the problems that we had encountered last class. So during the recap session, I will probably ask you guys to tell me what those problems were. So kind of be ready for that. And yeah, hey, good evening, Deepit. Glad you could join in. Cool. So let's wait for a couple of minutes for more people to join in and we can get started. Right. By the way, today is supposed to be Buddha Purnima or something. So, any Buddhists in the audience, wish you a very happy festival. All right. Cool. So far, so good. No shocks in the stable. The connection is stable. Okay, that's good. Hey, good evening, Arun. Glad you could join in. Cool. Good evening, Tim. Hmm. It has started raining a lot in Bangalore, right? Anyone who is still in Bangalore, uh, must be raining a lot over there. Okay, Arun says, I have a query regarding assignment question. At last I can ask. Okay, sure, Arun. I'll be happy to help you with that. Can you just give me the name of the question in case this thing? Vishwaroop is asking me, where am I visiting? I'm visiting Manali. So I'm actually in Manali right now with a few of my friends. It's been a long time since I took a break. So I thought it would be nice to come here. Okay. Yeah, at least it's bringing the heat down. Totally agree, man. So I have family who is in Bangalore, so they were telling me that it's a welcome change. So yeah, yeah. Okay, a lot of people are happy that I'm in Manali. Yeah, that sort of explains the sweater, right? That you've been seeing for the last few classes. It's kind of really, really cold here. So yeah. And for a change, like I'm doing hikes and stuff, it's helping me with my health a bit. Like I had really, really gotten this thing. No, no, no. I didn't bike here. I traveled the usual way. I took a flight to Chandigarh, and from Chandigarh, I took a bus to Manali. Yeah. Okay, hidden state is the question name. Okay, sure, Arun. We'll take a look. So actually, I had a couple of questions. Some other people had asked me. I just wanted to see if it was the same question. Hidden states is something I've not seen. We will take a look at it. We'll take a look at it. All right. Request you to just put a question on the questions tab so that it's easy for me to remember that we have to do this. Okay, guys. So let's begin with our lecture on long short-term memory. Uh, if you guys recall the discussion that we had last class, right? Last class we had seen this new neural network architecture called an RNN, right? A recurrent neural network. What was nice about this neural network architecture is that now there is some explicit tensor which is storing contextual information, right? If you remember our discussion last class, this tensor ht minus 1 and ht, these two tensors are tensors which explicitly store what is it that my network has to remember about the context from the previous words, right? One of the major problems with the methods that we had studied before was that there was no explicit way for us to capture contextual information. And even if there was a way for us to capture contextual information, it was very, very computationally expensive. What am I talking about, by the way? What is computationally expensive but can capture some context information? Can you guys remind me quickly? What is that technique called in NLP? Anyone? N-grams, perfect, right? N-grams is the right answer. Vishwarup, skipgram isn't the right answer. Skipgram is something which allows us to embed, to get vectors out of words, right? That is different from N-grams. So skipgram is correct if you're talking about embeddings, but it doesn't really help us capture contextual information so much, right? N-grams is kind of the answer I was after. So cool. Anyway, this network seems to solve that problem because of this hidden state. And this hidden state can be thought of as introducing some memory inside our neural network, right? I hope you guys remember that discussion. So let's sort of go through the broad things that we have to recall before we can resume our discussion of Lstms. Okay. First of all, what problems do recurrent neural networks solve? They solve two major problems with respect to the word-to-vec kind of architectures. First of all, they allow for variable input and output lengths. We saw this. For different lengths of the input, we will have different number of hidden states which will be generated because of the loop that is there inside this architecture, right? So that is problem number one that it solves. Problem number two that it solves is explicit encoding of context, which is the hidden state, which is the memory, right? So these are the problems that it kind of solves. The types of RNNs that we saw last class was one-to-one, one-to-many, many-to-one, many-to-many, right? Do you guys broadly remember the applications of these? So for example, one-to-one would be our normal neural network architecture, right? One-to-one is our normal feed-forward kind of architecture. One-to-many, can you guys quickly remind me? Where can I apply a one-to-many kind of, this thing, RNN? I can apply it for essay writing. If I give you a topic, you have to give me a sentence. For those kinds of tasks, I can use a one-to-many kind of architecture. Then we have many-to-one architectures. Anyone can remind me? This is for topic modeling, right? If I give you a bunch of text, you have to tell me broadly which category it falls under, right? Okay. And finally, many-to-many is what we saw in the last class, which was kind of complicated, right? In fact, we saw two versions of it. So summarization is one problem and parts of speech tagging is another type, right? So if we do not give any delay between the input and the output, that kind of an architecture will be useful for parts of speech tagging, as Indradeep has rightly mentioned. And if we introduce a delay, like if I tell my network, don't start generating till you've seen the entire input, that can be used for a kind of summarization kind of application, right? So today we're going to go slightly in depth into the summarization side. We're going to see a kind of architecture where we first provide the input text, then we ask this network to generate an output summary. Okay. So it becomes important for us to first show the entire text to the network and then come up with a summary of that text. Okay, cool. Finally, one last thing. How did we train this neural network? We applied a concept which is known as backpropagation through time. If you guys remember, this had caused certain problems for us, right? The backpropagation through time had caused a couple of problems which we had detected last class. So we will elaborate those as we go along, right? Okay. So today the agenda is as follows. We're going to study this new architecture which is going to solve the problems. Okay. The major problem it's going to solve is that of vanishing and exploding gradients. This is the name of the problem, uh, which we saw while we were studying this backpropagation through time algorithm last class, right? So we're going to see how long short-term memory is going to take care of this problem broadly. So that is the motivation behind this architecture. The application we're going to study is text summarization. And towards this application, we're going to come across a few concepts. So let's go through them quickly. We're going to develop something which is known as an encoder decoder architecture. Don't be afraid of the new name. This is nothing but that many to many kind of RNN that we saw last class, where we have a delay, right? So if we have a many to many architecture where there is some sort of delay, that becomes something which is known as an encoder decoder architecture. Okay, we're going to study how to set this up. We're going to see the functions of these three special gates which are there in this LSTM model. Okay, so we're going to see that in detail. Once we study this, we're going to try and see if we can simplify this architecture. So a simplified version of this is known as the gated recurrent unit. We're going to go into depth of that. I remember last class somebody had asked me, are we going to do this with peepholes? So I will discuss the peephole variant also, like with you. So the person who asked me the question last class, you'll get your answer today. And finally, we're going to see the root score. Okay, there is something which is known as root score, which basically gives us a way to judge whether the summary is good enough or not. Okay, so we're going to study how this root score is decided and how we can use this to check whether our summaries which are generated are good or not. Okay, so that's the broad agenda for today. Before we go, of course, we're going to have to discuss what the industry requirement is. Once we understand the industry requirement, we can go ahead and try and solve the problem with all the concepts that we'll learn, right? As usual, this is going to be the structure of the class. So without further delay, let's go and see the problem that is there. Okay. Before I go for the problem, guys, there is a couple of questions which are coming to me. Let me just check, address those. RNN predicts the next word given in a sentence. How is that useful in text classification? Okay. So Vishwarup, do you remember how in computer vision, we first teach a network how to do object detection? Then we can cut out a part of that and then use that for other tasks, right? In the same way, if we get an RNN to basically predict the next word in a given sentence, along the way, that hidden state that is there, right? That will encode some useful information which is useful for other things. So predicting, although in the last class, right, the example that I had shown you, the loss function that I had used was categorical cross entropy. So if you remember last class, we were doing a many to one kind of architecture. And because we use categorical cross entropy, we were not asking our network to predict the next word, right? We were actually not asking our network to predict the next word. So, but when we come to BERT, right, you will see that in BERT, we will ask it to predict something. If I remember correctly, BERT, we will basically see how to generate embeddings which are generalizable, right? So maybe this kind of discussion we can carry out when we come to BERT model. Cool. So that's how. Okay. Now let's see the problem statement for today, guys. Are you guys aware of this app called InShots? So it was a really popular app. In fact, I had used it. It had come through Yahoo News. Like it was inspired by Yahoo News. Okay. So the Yahoo News division had a way to summarize things, and InShots sort of took that idea and ran with it. So InShots essentially gives you a very quick summary. It's like those cue cards, right? So just like we have, so if you've used any of these dating apps, you'll know something about left swipe, right swipe. So InShots also had some sort of left swipe, right swipe thing where you kept swiping the card and it will give you a new piece of news with a summary of what that headline is, right? So that is what InShots was. What we are going to try and do is we're going to try and automate the process of InShots. We're going to not pay journalists to sit and summarize it. We're going to try and get a machine to do this for us, right? Okay. So generally what we have to do is, so let's understand the problem of text summarization, right? Essentially, we will be given a news article or something which is 40 to 60 words in length, and we have to summarize it to something which is less than 30 words. Okay. So at least for today's problem setting, I know this is not exactly like InShots, but for today's problem, the toy problem that we're going to solve using the concepts for today, we're going to take as input a text string which has 40 to 60 words, and we have to provide a summary which is 30 words or less. Okay, that is the setting for today. So this is sort of stored in this config dictionary. So let's understand this dictionary. It will become important later. Okay. So I'm requiring the min text length of the input articles to be 40. I'm setting the max text length to 60. This is mainly being done because uh, if you guys notice, right, the more input you give to your network, the more memory you will occupy. So the limitation that we have here is we have to work with the free GPU that we have been given, right? So it becomes kind of difficult to go beyond 60 words and keep into that GPU memory. If you want to do much higher predictions, you'll require much better GPUs, right? So this choice was basically done because we wanted to optimize the memory that is available to us for free, right? So we are sort of selecting articles which are between 40 to 60 words in length. We are fixing a max summary length to 30. So basically, when we ask our network to generate a summary, we're going to say, boss, if you cross 30 words, don't do it anymore, stop. Okay. It's a hard stop that we're putting so that we don't give too long summaries, right? We don't want stories. We just want the crux of the article here. We are also defining the latent dimension and the embedding dimension. Uh, in this figure, can you guys quickly remind me what would the latent dimension be? If I say latent dimension, which vector's dimension am I talking about here with respect to RNNs? HT, right? Of course. The hidden state, this is what I'm calling the latent dimension. Why latent? The word latent means hidden, right? So latent dimension is 300. So now we're going to set the hidden dimensions length as 300 wherever we are going to use it. And the embedding dimension. What is the embedding? Uh, which vector over here is the embedding? Okay, xt is the embedding, right? Perfect. So the embedding dimension we're going to set to 200. This is the convention that we're going to use. Again, these numbers were chosen because we had to get things to work on a limited GPU. Okay. So what I would request you guys to do is probably play around with this and see how it affects your GPU memory, because that is one of the practical things when it comes to NLP, right? We have to sort of manage GPU memory and all that. So I would like you to try increasing this and see where it fails. That would be a fun thing to try out. So anyway, let's move on. So let's understand our data set a little bit better. Okay. Now that we have understood what our configuration is, let's understand the data set. So I essentially have these news summary.csv and news summary more.csv. So I essentially have these two data sources. Essentially, what I'm doing here is this news summary.csv has a column which is known as headlines. Okay. I'm going to use the headlines of that article as a substitute for the summary. Am I allowed to do this? So usually when we read an article, right, the headline sort of captures a pretty decent summary of the entire article, right? So the headline is what I'm going to substitute as my summary here. So I'm not actually training on a good data set of InShorts where there are 60 word summaries of long articles. I'm not doing that kind of training. I'm taking news articles. I'm asking my network to summarize the headlines of that. Okay. And I'm hoping that this will sort of allow me to build something which can summarize other documents also, right? That's the hope. So let's see how well we do here. Similarly, over here, headlines, again, I'm going to call it summary. I'm simply renaming this headlines column to summary. That's all I'm doing in these two lines. And finally, I'm concatenating these raw and summary data frames to get my final training data set. Okay. So once I do this, the number of articles that I have are over here. Okay. I have 98,401 articles over here. So this is the raw things shape. Summary shape was 4,514. So the sum of these two is what I have inside this data frame. Okay. Again, we have two columns. One is the article, the other is the headline. Okay, cool. So before we go ahead, let's again see the distribution of the lengths of words of these articles. Okay. So this is the exploratory data analysis I'm doing. What I'm doing here is I'm basically taking this raw data frame, I'm converting it into individual words. I'm converting those back to a string and I'm looking at the length of that, right? So once I do this, it looks like the median length is kind of close to 60, right? Yeah. Oh, okay. Arun, so guys, one moment. Before I move ahead over here, Arun is asking me to repeat something. I'll repeat this. So headline is summary. So Arun, the data set that I have is news summary, right? This data set essentially contains the article and the headline. I'm using the headline of the article as a substitute for the summary because I don't have a good enough data set available where people have read through an article and summarized it, right? So the hack that we're using here is we are going to use the headline of the article as the summary. Is that clear? Okay, perfect. So now let's move on. All I'm doing here is now I'm showing you what are the typical lengths inside these data frames, right? We have to understand what the lengths of our articles look like. So let's kind of go through this quickly. If you notice here, the median length of this raw data frame, right? The median length of this raw data frame is close to 60. The interquartile range is over here, and there seem to be a lot of outliers. There are some articles which have almost zero. So this is clearly an outlier, right? It's probably a noisy thing. And then we have one article which has much more than 80 words. So somewhere between 80 to 100 words this article has. So these are the outliers. Similarly, for the summary data set, right? For the summary data set, okay, I think, okay, 1 minute. So we sort of generated this properly. It was, sorry, 1 moment. Okay, raw.summary. Okay. So just 1 moment. Let me remove this. Yeah, this is the correct code which was run. I don't know how that happened. I think that was a typo. Let's ignore that. Coming here, the summary data set, right? I have two data sets here. The summary's lengths look like this. The median length seems to be somewhere around 10. The summary column. So 1 moment. Right. My bad. What I'm looking at over here is the summary column of the raw data frame, right? So these are essentially the lengths of the headlines that are available to me. So my article lengths range anywhere from 0 to more than 80. My headline lengths range somewhere from 0 to 17.5. So 18. So 18 words looks like. Okay. So now what we're going to do is we're going to apply that filter that we had decided over here, right? We're going to now filter those articles out which have lengths less than 40 and lengths greater than 60. We're simply going to get rid of those, and whatever remains, we're going to use that for training. Okay. So all I'm doing here, if you notice in this code cell, is I'm applying this condition over here. So I'm basically saying you remove all the things which have length which is greater than this min length, and you remove all the things which have length less than this max length. Okay. Once I apply this, after filtering, the number of articles that survive are 54,572. So we still have quite a few articles to train with. Okay. 54,572 news articles we have, along with the summary that we have, right? Okay. So now let us sort of see the distribution of lengths after this filtering. So now our median seems to be somewhere close to 57 words, and we still have some outliers based on our analysis, but it looks like most of the article lengths are close to 50 words, right? And most of the summary lengths are close to 9 words over here, right? That is what we infer from this. Let's quickly take a look at the sample. So the text over here is India recorded their lowest ODI total in New Zealand after getting all out for more than 92 runs in 30.5 overs. In the fourth ODI at Hamilton on Thursday, 7 of India's batsmen were dismissed for single-digit scores, while the number 10 batsman Yuzvendra Chahal top scored with 18 runs out of 37 balls. I believe that is how you interpret this. India's previous lowest ODI total in New Zealand was 108. Okay. So basically, this is an article about a really bad match that India played in New Zealand. So the summary is India gets all out for 92, their lowest ODI total in New Zealand. Right? Does that seem like a reasonable summary of this? Previously, it was 108. Now we know that the new lowest score is 92. So this summary which is there, it captures all the essential information which is there in the text. Right? So the text length here was 56. The summary length was 13. What we have to do, we have to get our network to read this and generate this. Okay. So hope the problem statement is kind of clear now. Okay. The problem statement is clear now. Any doubts about the data, the problem, please ask me right away. Otherwise, we will go into the discussion of the architecture and stuff like that. Okay. Looks like there are no doubts. So let's proceed. Once again, what kind of problem is this? It falls under the many-to-many category, right? Like we discussed in during our recap. This is a many-to-many type of RNN problem. Why? Because the input is a sequence, the output is also a sequence, right? That is the whole meaning of many-to-many kind of problems. So the kind of architecture which works well for this is known as an encoder-decoder architecture. Okay, so this is like slightly more detail on top of the many-to-many architecture that we saw in the last class, right? So essentially, what I have here is this encoder network here is responsible for encoding the text which is there over here, right? So 56 words, there will be 56 hidden states for this particular example inside our encoder architecture. Everyone okay with this? Any doubts as to why this will be 56 for this example? No doubts there, right? Guys? Okay, no doubts. Let's proceed. So once I have actually done the encoding of my text article, right? Once I've done the encoding of my text article, I'm going to give the hidden state of this RNN to my decoder. Okay, so the main communication that is happening between the encoder and the decoder architecture is simply through the hidden state. The decoder architecture is never going to see the word embeddings directly. Okay, and this is what makes it interesting. So this is what we call the memory of the network, right? So it's like we're asking the encoder to read the sentence. Yeah, Ajay, you're right. Okay, but essentially we're asking this encoder to read the sentence and encode the important information inside the hidden state of that. Then this encoder hidden state is passed to the decoder, and the decoder has to take this hidden state and generate something based on it. Okay, so if you notice, the whole crux of the article, once you pass it through the encoder, will be in this hidden state. Okay, that is the main observation that we have to do here. Okay, if we use the vanilla RNN from last class, what would be the problem here basically? Did we notice that it would not be able to capture long range dependencies? Do we remember that discussion? Do you guys remember? Or if you don't remember, you can ask me. I will quickly do a recap of that. If not, we can proceed, right? Okay. So the main problem that, okay, Vikas wants a recap. Vikas, let's recap. All right, cool. So let's quickly go for the recap over here, right? In the last class, okay. So first, let me do a quick recap of what we discussed last class. Then we will come back to Lstm, right? And then Sean, I will answer your question. Just give me a couple of minutes. I want to do a recap first. So in the last class, guys, when we were studying the RNN architecture, right? We saw that there were two fundamental problems with it. The problems were vanishing or exploding gradients. So broadly speaking, this problem was occurring because in our architecture and in our RNN architecture, right, we have this thing here called the tanh. Okay. So can you guys quickly remind me what is the range of values that the tanh allows to pass? What is the range of values that it allows? It allows values from -1 to 1. Yes, it allows values from -1 to 1, but the gradients of this are in what range? 0 to 1, right? 0 to 1. Okay. So because of this tanh and because the values of the tanh are going to keep appearing in our gradient equation, right? So if you remember last class, we had seen how to do the back propagation of this architecture. The equation looks like this. What I want you guys to imagine is, in this equation, if I keep multiplying many small numbers between 0 and 1, that gradient is now going to go towards 0, right? We're quite comfortable with this idea. You take many small numbers and multiply them together, eventually it will drop down to 0. Okay. Now, if we decided to solve this problem by replacing tanh with something like a ReLU, right? In a ReLU, there is no limit on the gradients thing. So in a ReLU, right? For a ReLU, the gradient can be between, so the gradient for a ReLU can be between -infinity and infinity, right? It can be anywhere in this range. So if we now take many large numbers, okay, if we take many large numbers and we start multiplying them together, we will eventually reach infinity, right? Either infinity or -infinity. We will reach one of these two places. Now, of course, in computer systems, it is not possible to represent infinity, right? So beyond a certain number, we simply give up and say, we say not a number, right? So in our neural network training, we will see these nans which start appearing. So that is the problem of exploding gradients, okay? So the problem of vanishing gradients happens when we have tanh. The problem of exploding gradients happens when we have ReLU. And the basic problem here is, because of these architectural choices, right? Because of this nonlinearity here, it becomes kind of difficult to train this network. Okay, that is the implementation aspect. Now let's talk about the conceptual aspect, right? Okay, now when we have a tanh over here, I want you guys to understand something here. If you notice the lowest thing over here, right? The lowest thing over here captures the contribution of this word t minus 5 to the gradient of this w. Okay, w is a matrix which is there in our architecture. Okay, w is a matrix which appears somewhere here, I believe, right? So w matrix appears here, v matrix appears here, and u matrix appears there. So in our architecture, at a conceptual level, the contribution that is coming to the gradient of W from the fifth word from the end, right? The fifth word from the end, that is going to be very low. Why is it going to be very low? Because you already have these numbers which are between 0 and 1 sitting there, right? So they will reduce the importance of this word in that contribution. So do you guys see how this is like forgetting the old words? Is this idea clear? Like now it is like, because of that 0-1 relation, we are reducing the importance of old words. So contextual information from the early parts of your sentences will be lost. Contextual information will only be kept from the later part of your sentences. So this is the conceptual problem with this. Okay, this RNN architecture which we studied last class cannot handle long range dependencies. Okay, that's the idea here. So the question is, how do we solve this problem, right? How do we solve this problem? For that, we're going to start discussing the LSTM architecture, okay? The whole point of the LSTM architecture is to solve this problem of not being able to capture long-range dependencies. Cool. Now let me address the second question. So one moment, I'll quickly ask Vikas. Vikas, I hope the recap was good enough. Just let me know. Okay. And now let me quickly discuss Sean's question. One thing I wanted to ask for encoder decoder architecture. We encode or crunch the output and then feed the output from the encoder to the decoder to reconstruct the input given to the encoder. Okay. So Sean's question is, shouldn't we also feed the output of this to the decoder? Why are we just giving the hidden states? So Sean, there are multiple ways of doing this, but the earliest LSTM architectures only allowed this kind of communication between these two, okay? Because they felt we want this to capture most of the information. There are going to be variants which allow me to pass all the outputs here also, right? But for today's discussion, we're going to limit ourselves to this kind of architecture where only the hidden states is how we're communicating between them. Is that okay? Is that okay? Okay. Okay. So usually the encoder decoder architecture goes like, I'm giving all the output states to this, right? But the variant that we're studying today, the LSTM, in fact, the LSTM layer, which is over here, right? The way it is typically done in Keras is you only give the final memory states to this. So we'll discuss this when we come to the code part. Okay. So yeah, let's sort of delay till then. Yeah. Cool. So now let us try and understand what is the meaning of this long-term dependency that I'm talking about. Okay. So I want to sort of read out this sentence, this like paragraph. It is a bit long, so please follow along. I visited Paris last year during winter as a part of the business trip. For the first 2 months, I suffered from jet lag and stayed at a hotel near my office location. The weather was too cold for someone from a subcontinent. The trip lasted for 2 weeks and I traveled by metro for the most of my commute as the city is well connected. There were quite a lot of market areas for shopping and buying souvenirs as well. During the weekend, I even got a chance to see the Eiffel Tower. Okay. Now, the long range dependency that we want over here is the dependency between this Eiffel Tower word and Paris word, right? Why is this so? Because we all know the Eiffel Tower is a monument which is there in Paris. Okay. So let us say I want to summarize an article. Uh, Essentially, if I'm including the word Paris, I essentially also wanted to include the word Eiffel Tower, right? Because it's a salient point of that city. So the long range dependence that we're talking about here is the dependence between this phrase, which is Eiffel Tower, and this word, which is Paris. Okay, that is what we want. Now, if you guys imagine, if you let us kind of count the distance, okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, let us say that the distance in words, let us say the number of words which are there between this Paris and Eiffel Tower are close to 60 words. Okay, in fact, I can get this right. Let's actually count this. We can do this with a word counter. Okay, so there are 87 words between Paris and Eiffel Tower. Imagine if I took a very small number and I raised it to the power 87. Okay, let's do that, right? I'll take 0.99 and I'll raise it to power 87. It becomes zero point 0.4. So there's a huge reduction in the weightage that is given to the word Paris by the time I reach the word Eiffel Tower in my architecture, right? Because of the problem of that vanishing gradients. So we have to now modify our architecture so that this does not happen anymore. Okay. So let us quickly see what is the modification that we can do so that uh, this doesn't happen anymore. Okay. How do we overcome this? So first, let us discuss some strategies without changing the architecture, and then let's go for architecture changes. Okay. So some of the ways people dealt with this problem was they did something which is known as truncated backpropagation through time. The another way is to do gradient clipping. When will gradient clipping be useful, by the way, guys? Will it be useful for vanishing or exploding? Which case will it be useful for? Gradient clipping? Exploding gradient, right? Yeah. No, not both. It will be useful in the exploding gradient case because gradient clipping basically means if the gradient is above a certain number, you bring it to this number, okay, forcefully restricting the maximum value that this gradient can have. So gradient clipping is a concept that will help us in the exploding gradients case, okay. Then there is weight initialization. That basically means you initialize your weights in a way that that problem doesn't occur. This is a very common way of doing it. And finally, we'll go and study Lstm. This is the most effective out of all of these strategies. Okay, this is the most efficient. Okay. So Indradev's question to me is, but we can also clip when the gradient is less than the threshold, right? We can, but let me think about this. What if I restrict the minimum value of my gradient, right? If I restrict the minimum value of my gradient, it may cause noise, right, Indradeep? See, it's okay to restrict the maximum value of your numbers, but restricting the minimum value causes some problems, right? So let me think about this. Can we apply gradient clipping to solve the vanishing gradients problem? I have not seen it used in that way because we're okay with the zero gradient, right? In fact, we rely on zero gradient to cause convergence. So gradient going to zero is something we want. We don't want it to forcefully update when the actual contribution is low, right? Yeah. So no, Amit, it's the opposite. It will update the word weight forcefully. So if we force the gradients, if we clip it below, right, it will never converge. If you think about it, right, it will never converge. We will forcefully update our weights every time. So that's problematic. So there's a good reason why we don't do clipping below. We typically just clip above. Yeah. So let me quickly see the comments that the others have put. Arun says we may get bias and like falsely giving importance to unimportant words. Exactly, Arun, right? Exactly. Perfect intuition. We may get bias of unimportant words. Yes. Amit says it will remain constant. Yeah. So it will cause, in fact, Amit, it's the opposite, right? It will forcefully ask you to update your gradients. Even when the contribution is zero, you're saying, no, I want the contribution to be 0.2. That's wrong. Okay. So that's why we only clip above. Okay. Coming back, let's quickly talk about this truncated backpropagation algorithm. Okay. So intuitively, guys, what do you think? What do you think truncated backpropagation is? Anyone wants to take a wild guess as to what this could be? It's a very simple idea, right? Typically, when I calculate the gradients, I'm looking at the contribution from all the hidden states that are there. In the truncated case, I can simply choose a window. Okay, I can say I only want to update the gradient for the last 5 words. I don't care about the words before that. Just keep the last 5 words gradients every time I'm updating these weights. Right? That is the idea behind truncated backpropagation. I'm forcing it to only pick up gradient contributions from the last k words where I have the freedom to choose that k. The window size I can totally choose however I want, right? What is the obvious problem here? What is the obvious problem with doing truncated backpropagation? Obvious problem. Let us say I set the k to long-term context is lost. Yes, that is the core problem, right? Window decision is something we're used to, Arun, by now, right? We are used to hyperparameters. We do hyperparameter tuning. All that is there. We're okay with that. Window size will affect the long range corrections. That I can agree with. But the core problem over here is that we're forcefully not letting our network look at long-term contexts. For here, this extreme example, we had 87 words, right? In this Paris wala example, we had 87 words distance. So that can no longer be captured over here. So we don't want to do that. Okay, we don't want to do that. So instead now, let us ask ourselves, can we do some sort of change to our architecture so that we are able to solve both problems. We're able to keep long-term context as well, and we won't run into these exploding or vanishing gradients type of situations. Okay. So now let us kind of look at the LSTM architecture. Okay, cool. So just one moment. There is one particular figure that I want to focus on. Let's kind of take this figure. This is what we should understand first, and then we can move on with the details. Right? Okay. So let us now understand the basic concept behind LSTMs. Okay, cool. So what was the problem, guys? We were not able to capture long-term information. We were only able to capture short-term information. What is the obvious solution? If my memory is not enough, add more memory, right? Everybody solves memory issues on phones or devices that way, right? Simply add more memory. That is exactly what we're doing over here, okay? Now, we're going to have like two hidden states. One hidden state is only going to capture the short-term information, okay? This hidden state that I have here, ht minus 1, is only going to capture short-term information. This cell state that I have over here is only going to capture long-term information. Okay. So the basic strategy here is if my network is not having long-term memory, I will create some additional memory which can explicitly capture that long-term information. Okay. The whole game now is deciding how to use this hidden state. Okay. How to use this hidden state to add or subtract information from this long-term context, right? This long-term memory. Okay. So broadly speaking, the problem was we don't have long-term memory. The solution is we will add memory and call it long-term memory, and we will control how information flows into that long-term memory. Okay. So at a conceptual level, is everyone with me? At a conceptual level, do you know the basic difference between RNNs and LSTMs? Cool. Two people have agreed. I sincerely hope the others have as well. Okay. I hope you have understood this. The idea is simple. In RNNs, I had one hidden state. Now I'll have two hidden states. Yeah. The other hidden state I'm going to call cell state, and this cell state is going to carry long-term information. Okay. So now let us see how this is actually done. Right? Let's kind of see how this is actually done. So at a conceptual level, this is the change that we're going to do. Oops, just one moment. So the conceptual change is this. Add memory to store long-term information. Okay. And now let us see how this is practically achieved. Practical implementation. All right. Cool. So just like last time, I'm going to bring in a diagram over here of the architecture. Once we have the diagram, we'll analyze that and we will go step by step and see how this works. Okay. Cool. Okay. So this is what an LSTM architecture looks like. Does it look scary to you guys? Does this look scary? When I first saw it, I was a bit scared. But it's kind of very logical, guys. It's very logical. No need to worry. Okay. If you have understood, if you followed my explanation for the RNN last class, right? The same way we can the same way we can debug this. Okay. So guys, so I think fear comes because we don't know what is important and what is not important, right? So I'll tell you my solution. As a researcher, the important information about these concepts that you have to know are what is the architecture, what problem the architecture solves, and how effective is it. If you know these three things about architectures, you should be confident. Okay. So this fear is being caused because you don't know what's important, what's not important, right? These three questions you should be able to answer. What is the architecture? Why is the architecture? And how effective is it? Right? Okay. Some people are telling me matrix multiplication scares you. Nothing to be scared of. It's a computation which the computer can do for you. NumPy. Whatever NumPy gives you, that is enough. Hmm. Okay. Nice. I see. I see. No need to worry. No need to worry. See, the math, the beautiful thing about software is you don't have to know the math to get this stuff done, right? You only have to understand how to use the software. As long as you know how to use the software and as long as you can answer these three questions about your architecture, you're good. Okay. So let's now focus on answering these three questions in our architecture. Okay. First question. What is the architecture? The answer is on this page. The second question is, why is this architecture? We already saw this, right? We already saw this. The architecture's why is because we now want to carry long-term information. And how effective is it? That we will understand by the implementation that we're going to discuss in the last class. If we focus on this, then we are good enough to go. Okay, that's my promise to you. So let's now focus on the first question. What is the architecture? Okay. So if you guys remember, the xt is nothing but the input, right, to our input word in our task, right? What is our task? We have to basically do summarization. So one LSTM unit which is reading the sentence. So imagine the network is now reading a sentence. The xt over here is the input word at time step t. Okay. Any doubts about what this means? So any doubts about what this means? I just want to remind you once. So I have a fat cat, right? If I have this sentence, then the t that I have over here is going to be 1, 2, 3, 4, 5, right? Okay. So what I mean over here is the first time I'm going to feed the word I, second time I'm going to feed the word have, then a, then fat, then cat. So this input word at time step t is nothing but the input word over here. Okay, cool. How are we sending the input word? Are we sending a string to our network or are we doing something with it? What did we do in the RNN case? How did we provide this? Did we have to convert our word uh, into some sort of vector? Yeah, I have to convert it to a vector. So the word to vec encoding, word to vec embedding of this word is what I would feed, right? So I'm going to take my word first. I'm going to get its one hot encoded representation. This one hot encoded representation, I'm going to convert to a word to vec representation. And I have full freedom to use pre-trained word to vec weights. Okay. Added a layer which was trainable over the course of our training, right? We had this embedding layer. So just want to remind you, we had this keras.embedding last class, right? So we actually learned the embedding layer during training. So we had both options. We can either do word to vec or we can learn this on the fly. So today, for today's discussion, what we're going to do is we're going to do what we did last class. We're not going to take pre-trained word to vec. We're going to take embeddings. Okay. So let's understand this part very clearly again. I have a word. Okay. I have a word. I'm going to pass it through an embedding layer. And I'm going to get a vector, right? I'm going to get a vector. So if I'm passing this word I, what is this x? Is this x1? Can I call this x1? This vector? Okay, I can call this x1. Same way, if I take this have and I pass it through the embedding, what I will get is x2. If I take this and I pass it to the embedding, what I will get is x3 and so on. Okay, so this xt that I'm giving to this LSTM is nothing but the embedding. Any doubts so far? There should be no doubts here, right? The input is a vector. Cool. So now let's move on. Then, just like last class, just like the RNN, we have to give an input ht minus 1. Okay. Do you guys remember the discussion we had last class? I have many options for setting this at the 0th word, right? At the 0th position, like at the start of my sentence, I have many options. First option is I can initialize it with zeros. Okay. The second option is I can initialize with the random every time, or I can initialize it with a fixed random. Yeah, these are the three options, right? So guys, in the case of LSTMs, right, people actually prefer the zeros way. So they tried all three strategies. In the case of RNNs, they typically use the fixed random vectors, but in the case of LSTMs, they prefer to use an initial state of 0. Same way, so the same way we had this discussion for this hidden state, right? The same applies for the C, okay? From now on, I want you to think of this C vector over here as just another hidden state. Whatever discussion we did last class on this hidden state can sort of carry over for this, okay? So again, to give the first CT, right, C0, let's call it C0. The first long-term memory state that I have three options. For LSTMs, again, we will go with the zero strategy. This is preferred. Okay. Okay. So now these three things are taken care of in our architecture. XT is the embedding of the input word. HT minus 1 is something which we initialize to 0. CT minus 1 is also something we initialize to 0 at the 0th word. Okay. So this is what we have. Anil says for RNNs we use zeros too, right? Yes. So in the coding example last class we use zeros. But in the case of RNNs, people found that it's actually better to sometimes use a fixed random in some cases because it will solve that symmetry problem in neural networks, right? So the computation of a RNN was very simple. So putting this as 0 would make a lot of things 0 over here. It would make the contribution over here 0, right? So we will always end up ignoring the first word if we put this as 0. That's the problem. If you think about it, Anil. You multiply this W with a 0 vector, it will give you 0, right? So that is the issue. We cannot keep it 0 all the time for RNNs, but in LSTMs, we prefer this. In the case of LSTMs, we prefer using 0 over there. Okay. Are we okay so far? Guys, we have taken care of these three inputs to our architecture. Cool. Now let's proceed. Now I have this XT, and now there is very complicated things going on, right? So now let me explain to you what each of these are. Okay, I'll now explain to you what each of these things are. So let me put that on a separate page. Okay, let me actually do this on a separate page. Okay. So the correct way to understand this is to take these structures and sort of classify them. Okay. Arun's question is, what is the change here? Like, why not fixed for LSTM mathematically? You will see, Arun. We're going to come across this when we see the encoder decoder architecture, right? You will see why this choice is made for the encoder. You'll see that. I'll address this. Okay, cool. For now, what I want to do is I want to make it easy for you to remember what each of these components are. Okay. So first, let me draw a nice box around this component. This is component number 1. Okay. I will put a box around this second component, right? I will call this component number 2, and this final thing over here, I will call it component number 3. Okay. So now, to understand the computation that is going inside this LSTM cell, what we're going to do is we're going to break down this architecture into 3 parts, and we're going to understand the purpose of each of these 3 parts, right? That is how we're going to proceed with this. Okay. Okay. Sean has a question which he's asked me in private chat. Hey, Sean, can we deal with this later? This is not related to LSTMs in general, right? This is a more generic problem. So please put it up as a question on the questions tab. I will address this later. I don't want to break the flow right now. Okay, cool. So let's understand. We took this LSTM architecture. We understood the 3 inputs which are there. Now we are going to break this architecture down further, and we're going to understand the purpose of each of these things. Okay. So in pink, if you notice, whatever I have put in pink is basically my component number 1. This component is known as the forget gate. Okay. This component is known as the forget gate. The second component that I have over here is known as the input gate. Okay. And the third and final component that I have here is the output gate. Okay. So if we now break down this architecture into these 3 parts, it becomes much easier to understand why this is designed this way. Okay. So everyone clear so far? We have 3 components. Okay. 3 components, we're breaking this down, and we're going to study the use of each of these. Okay. We're going to study the use of each of these. And it's very, very nice and intuitive how we're going to use these things. Okay. So first, let us understand at a conceptual level what each of these 3 things mean. Okay, let's understand it at a conceptual level. Then we will come back to this architecture and see how it is actually being done. Okay, how it's actually being done. Okay, so let's understand this first at a conceptual level. Okay, so let us come back to our understanding of what this LSTM is trying to do, right? So let me draw one big line over here. I will call this my long-term memory. I will put this blue thing over here. I will call it short-term memory. And let us now define some good rules for how we can let information go from the short-term memory to the long-term memory. Okay, cool. So intuitively speaking, guys, can you tell me something? If you're reading a paragraph, we have all read novels at some point in our lives, right? We've all read storybooks and novels. I want you guys to remember what happens when you're reading a novel, right? So novels are basically divided into chapters, and to properly understand what the story means, right? It is important to remember things from chapter 1, chapter 2, chapter 3 when you're reading chapter 20, right? How what all information you got in the first few chapters is still relevant in the final chapter, right? So internally in your brain, there is something which is keeping track of what is being read just now. There is something which is then taking it to your long-term memory, so that later on when you're on chapter 20, you can access that long-term memory and say, oh, okay, there is a new character here. I think this character came into the story when our main character died, and now he's like the replacement, something like that, right? Some contextual information should be there. Yes, exactly. So let us now try and capture this idea. Okay. So now I want to think of this as a design problem. Okay. Now I want you to think of, I have this memory location somewhere in my computer, which is the long-term memory. I have some memory location, which is the short-term memory. Okay. My long-term memory is limited, my short-term memory is also limited. Okay. So at a fundamental level, what are the operations that we carry out with memory? What are the operations that we can carry out? So the basic operations that we want are as follows. Okay. The first operation that I want, addition, subtraction, insert, search. Perfect, guys. Perfect, perfect. Love the fact that you're able to relate these two things. Okay. So the first operation I'm going to take is the addition part or the insertion part, as Arun and Deepat have said. I first now need to define a way for my information to flow from short term to long term. Okay. I want to find a way to let information flow from the short term memory to the long term memory. How am I going to do that? I'm going to call this the input operation. Okay. What is the job of this input operation? Okay. What is the job of this input operation? Allow the job of this input operation is to allow info to flow from short term to long term. Okay, this is operation number one. Can I just keep, can this flow of information be one-sided? Can this flow of information be one-sided? Should I always take information from short term and keep putting it in long term, or should I put a limit there? It will overflow, right? Logically speaking, it will overflow. If I just keep storing things and I don't remove things from it, it will reach a limit and it will burst. Okay. So now to allow it to not burst, to make sure that the capacity of that memory is respected, we will now have to include one operation which is known as the subtract operation, right? Like Arun says, we need to have something which allows information to go away from that long-term memory. Something which is not relevant. Like, for example, let us say Game of Thrones, like characters die left, right, center, right? So it really doesn't make sense to keep remembering the names of characters who have already died. Okay. So things like that. So we now have to create a mechanism by which we can get our memory to forget stuff. Okay. So this operation I'm going to call as the forget operation. Okay. The job of this forget operation, yeah. Unless we have photogenic memory in hardware world. Yeah, Arun. To the best of my knowledge, we don't actually. So yeah, everything is finite, sadly. Okay, coming back. This is known as the forget operation. The job of this forget operation is to allow information. Let me make this more clear. Allow unnecessary information. Okay, unnecessary information to be removed from the long-term memory. Okay, cool. So this is an interesting rule, right? I'm not allowing my long-term memory to see my data and my input directly. The only way for my long-term memory to get information is through this input operation. The input operation requires you to take your short-term memory, do something to that, and then store it in the long term. Okay, that is the input operation. Then we have the forget operation, which allows me to manage the memory that is there over here. Manage the stuff which is important and the stuff which is not important inside this long-term memory. So that's why I need this forget information. Okay, cool. So the final operation, guys, what is the final operation? Okay, so I have stored information. I'm allowing my information to be managed. What is the actual purpose of this? Aren't we forgetting the fundamental need for this? Isn't the actual purpose of this memory to actually retrieve? Yeah, retrieval, right? Retrieval. So retrieving the information when it is necessary, that is the third operation, right? Okay. So I'll call this the output operation. Why output? Because I'm taking an output from the long-term memory. I basically now want to take some information which is there in my long-term memory, bring it to the current computation, and then do something with it to finally give some output, right? So that retrieval step, I'm going to call as the output operation. Okay. So the output operation's purpose is to retrieve information from long term. Okay. And the final thing here is I'm only going to allow things to go into my long-term memory from the short-term memory. I'm not going to allow it to directly interact with the data or the labels. Okay. This long-term memory has to be pristine. Okay. So if we now keep these three operations in mind, we can understand the purpose of each of these things. Okay. So the forget gate that you see here is nothing but this forget operation. Okay. The input gate that you see here is nothing but this input operation, and the output gate that you see here is nothing but the output operation. Okay. So let us now at a conceptual level get the understanding of these gates. The forget gate's job is to allow my long-term memory to remove information from it which is unnecessary. Ajay's question is, how do we decide this information is unnecessary? Ajay, we let the neural network decide while it is training. We are not going to do anything from our side. We are going to let gradient descent decide how to do this, right? Just like in computer vision, we didn't care about what weights were learned. We let gradient descent decide what weight should be there. We just set up the process and we let it figure out, right? So this is how we will do it here also. We will set up this process, we will set up this computation in a way that it can do this, and then we will forget about what is actually happening. Gradient descent will take care of it. Okay. So forget gates discussion is done. Our input gates job is to feed information from our short-term memory to our long-term memory. So all the computation that you see here will be in that sense. Okay. And finally, the output gate is something which is accessing the long-term memory. It is doing some operation on it. And finally, this operation is what allows it to give the final output. Okay. So broadly speaking, at a conceptual level, this is how this works. Any doubts with how this is set up? Does this seem logical to everyone? Does this way of doing things seem logical to everyone? Okay, cool. So once we come, so guys, this is a logical point also for a break. Let us take a break. Once we come back from the break, we will see these actual mathematical operations and we will see why they allow the network to do forgetting, why they allow the network to do inputting, and why they allow the network to do outputting. Okay. So the core math of what enables this process is what we will study after the break. But during the break, I will just leave the slide open. I want you guys to really internalize this, okay? The first part over here is the forget gate. The next part is the input gate. The final part is the output gate. So just want you guys to keep this in mind. I'm going to start the break timer now. I'll see you guys in 5 minutes. And we're back. Cool. One person seems to be back. Are you guys back as well? Uh, can you guys quickly hit the yes or no button? Nice. More people want to make me laugh today. Awesome. Cool. A lot of people are back. Interesting stuff, right? Now that we understand why this works, it kind of gets interesting. So let's go and study how this is done, right? Okay. So let's continue our discussion on this by starting by first focusing on this input gate, right? Like before we study how the forget gate works, it's important to understand how information is flowing into this long-term memory. So I would like to start my discussion by first looking at only the input gates functioning. Okay, so let's do that. So now our main focus is on the input gate, right? Okay. So let's see how the computation is happening here. Okay, input gate, how information flows into long-term memory. All right, so let's see this. So what you have to understand here basically is this path. Okay, so for the input gate, the path that we're going to focus on is what I'm now going to highlight here in yellow. Okay, right? Okay, so this is the path that we're going to follow. Okay, cool. So imagine now that this is the first LSTM unit in our architecture. Okay, what do I mean by first? We have just given the first input to our LSTM. That is what's happening over here. If this is the first one, can you guys quickly tell me what should C0 be? What should this be? Should C0 be? We just discussed this, right? Yeah, this should be the zero vector. So now my C0 is going to basically be a huge zero vector. The dimension of this vector is 300, if I remember correctly. In our config, we had set latent dimension to 300, right? So this is 300. Okay, so imagine this is a 300 length vector. If you multiply anything with zero, what does it become? Multiplying anything with zero will give you what? Zero only, right? So this multiplication operation right now is not going to do anything for us, right? So that is why we can safely ignore this for now. Okay, we can safely ignore this for now. This is going to do nothing to my C at the first word when I give the first word. Okay, cool. So now let us come and see how this zero vector is going to become something else, right? So if you guys notice here, there is an addition operation here. It basically means that I'm going to get a tensor from this part and I'm going to add it to the zero vector, right? So after this addition, whatever I'm going to get is whatever this tensor is, right? Whatever this tensor I'm going to get in through this yellow path, that only it's going to come there. So that is what we're going to focus on. Okay, so this is why this is a discussion of the input gate. Cool. So now let us see how the computation is happening. Okay, if you remember, this is our input word embedding. This is the input word embedding. This is the hidden state. This is the short-term memory hidden state. All right. Okay, so guys, whenever we come to this kind of a node in this diagram, right, whenever you see two lines joining, what you have to interpret this as is concatenation. Okay, so I know that last class, whenever lines were joining, it was addition, but in today's class, in this architecture, we have to interpret this as concatenation. What do I mean by concatenation? If I have a vector xt and I have a vector ht minus 1, right? Both of them are now row vectors. Imagine both of them are row vectors. If I simply take this and I attach this to this, won't I get a longer vector, the length of which is the sum of the lengths of these two vectors? It's going to be the sum of the lengths of these two vectors, right? So this operation is known as the concatenation operation. So if this guy was like 300 length, oh sorry, this guy was 200, no? Yeah, this is 200, this is 300. Then the output that we get after this operation is 500 length. Okay, so what I want you guys to imagine right now is, at this point, we're going to take this input embedding vector, we're going to take this zero vector, we're simply attaching both of them and we're passing this forward. Okay, so from now on, in this green part, whatever is flowing is this concatenated vector. Cool. Okay. Now let us come here. So again, we don't have to worry about this part for now because this is the part of the forget gate. Anyway, it's not going to do anything to my long-term memory. So it's okay if we totally ignore this section for now. Let us bring this concatenated vector here and take it over here. Okay, let's take it over here. Do you guys notice this matrix multiplication, Wi? In Keras, how do I implement matrix multiplication? How do I do this in Keras? Guys? Dense, right? I use the dense layer, exactly. So if I now take this concatenated layer, okay, and I multiply this Wi matrix with it, what will I get? I will simply get Wi times this concatenated vector xt comma ht minus 1, right? So this operation is nothing but a dense operation. Because it's a dense operation, we also have to add a bias term over here. Okay. So the bias term that I'm going to add over here, I'm going to call it bi. Why I? Because this is the bias term of the input gate. Okay. This is the bias term of the input gate. This is the weight matrix of the input operation. Okay. So this is what I'm getting here. Now I'm going to take this and I'm going to pass it through this sigmoid nonlinearity. Okay. Because there is a sigma, this is nothing but the sigmoid. Do we all remember what the sigmoid looks like? 0 to 1 range. Gradients are also between 0 to 1. Do we remember this? Guys? Okay. So this is, oh, okay. Sean is trying to make me laugh. Okay. Cool. So we remember this. So all I'm going to do here is I'm going to pass this whole thing through the sigmoid nonlinearity. And this output that I'm getting after this, I'm calling IT. Okay. This output I'm going to call as IT now. Oh, my bad. So, okay, let me just write it here. This is IT. Okay. The vector IT is obtained by taking this concatenated vector, multiplying it with Wi, adding Bi, putting it through a sigmoid and passing it along. Okay, cool. But do you notice that we have this other thing also here? Do you notice that the same concatenated vector is being passed forward here also to this WC, right? So now there is going to be another dense operation happening here, right? Do you guys see this? Now instead of Wi plus Bi, I'm going to do Wc plus Bc, right? This is the other dense operation that I'm going to apply. Okay. So let's note this down now. So this is now going to be this vector xt comma ht minus 1. Okay. I'm going to multiply this by this matrix WC. I'm going to add a bias term associated with this, which is BC. And then this I'm going to pass through a tan H. Okay. This I'm going to pass through a tan H. And the output of this operation, okay, the output of this operation, I'm going to call C tilde T. Okay, cool. So now let us understand this. Let us try and understand what this operation is. Do you guys see that this, structurally speaking, both operations are similar? The only difference is with the non-linearity over here, right? I have this concatenated vector. I'm basically doing one matrix operation over here, one matrix operation over here. The only difference between these two paths is the sigma and the tan H. Okay. So now let us try and qualitatively understand what is this sigma, what is this tan H's job. Okay. So let's first focus on this IT vector. This IT vector is the output of a sigmoid. So can you guys quickly tell me what are the range of values these vectors are going to have? Range of values 0 to 1. Okay. So this IT vector's output is going to be in the range of 0 to 1. Tan H is going to be what? Minus 1 to 1. Okay. Minus 1 comma 1. Okay. All right. Awesome. So now the question is, yeah. Now the question is, why did I choose to do 0 to 1 in one leg and minus 1 to 1 in another leg? Let's try and figure out why this is important. Okay, guys, let's figure out why this is important. I want you to now interpret this CT as the current estimate for long term. Okay, I want you to interpret this IT as current estimate of input info. Okay, cool. Now, the operation that we're seeing here, right, guys, this X that you see over here, this is actually an element-wise multiplication. Okay, this is an element-wise multiplication. So now let us sort of try and visualize what is happening at this stage. Okay, so the final output that I'm getting here, right? The final output that I'm getting here, let me call this as CT. Okay, let me call that as CT. Mathematically speaking, CT is equal to IT, sorry, this is IT and CT tilde into CT tilde, okay, where this is element wise. Okay, let's sort of visualize this with a quick example. Okay, let us say this is 0.1, 0.5, 0.3. Okay, something like this. This vector looks like this. Let us say CT tilde looks like minus 0.8, minus 0.3 and 0.7, right? Okay. So the main thing that you have to notice here is because we chose the nonlinearity of IT to be sigmoid, this IT cannot go below 0. So this IT has no power to change the sign of this CT tilde. Okay. The only thing I'm allowing my IT to do is to change the importance of these things, right? I can multiply every element inside this CT tilde with a number between 0 and 1. All that this IT is allowing me to do is change the relative importance of entries inside this CT. Okay. So now I want you guys to imagine this thing. I have decided what to store as my, I have decided on something that I want to store in my long-term memory. But this storage that is going there, I have to first see what I'm getting right now, right? I have to adjust the importance of the information that's flowing into my long-term memory based on how important it is in the current context. Okay. So that is the reasoning behind this input gate. Okay. I have this IT vector which can only do element-wise multiplication. It can only change the relative weightage of each of these entries, but the actual encoding of the direction, right? The sign is, is being captured by the CT vector. So that is why we can now think of this operation as I have my current estimate for long-term memory. I'm weighting this current estimate of long-term memory by the relative importance of my input. And then this product is what I'm going to now call my final long-term memory, right? Is this discussion clear to everyone? Quick check. Are you guys with me or have I lost you? I want you guys to think of this. Okay, I have lost you. Okay. Again, the 3 sentences. Okay, I'll quickly repeat this. Okay, I'll repeat this. Okay, cool. So the operation. So okay, let's sort of come back here and let us see this. Okay. What I have over here is my what to put in long term. Okay. This CT over here is context info from current world. Okay. This IT is now, so this guy over here. Oops, sorry. Yeah. So this guy over here is relative weights with respect to current input. Right? Okay. So cool. So let us now understand it from this point of view. What I'm storing in my long-term memory is a function of my current input and what I believe should be stored, right? So what I have is, I have this one part, this purple part that you're seeing here, right? this operation is basically capturing my information that I want to store in my long-term memory. What is the restriction that I'm placing on this? I'm allowing the range of these vectors to only be between 0 and -1 and 1. Why am I allowing it to be between -1 and 1? Because these kinds of vectors are basically able to capture angles, if you guys remember, right? So on a circle, if I wanted to define a unit vector, each entry of that unit vector would be between -1 and 1, correct? That would basically be my cos theta, if you guys remember. Yeah, geometrically, is that making sense? So think of this CT as a direction vector which is capturing the context information from my current word. Okay, I have encountered a word. I want to only capture the direction information from this, which is why I'm applying tan h over here. Now, I also want to give my network freedom to reweight this direction. I want to give some freedom for my network to decide what direction should have more importance, what direction should have less importance. So think of it this way. This is like my first guess. This is like a refinement on top of that, right? This is like my first guess of the direction. This is like a refinement on top of that. Why are we doing this two-stage business? We're doing this two-stage business because this helps us tackle the problem of vanishing gradients. How it helps us, we're going to see in the math. But basically, the input to our long-term memory comes out to be a two-step process. I will first make a random guess based on this computation, right? Based on this tan h computation, I'm going to make a random guess of the direction. Based on this sigmoid computation, I'm going to get one relative weight. Okay, the product of these two is what I'm going to store in my long-term memory, and this is how the input gate functions. Okay, let me quickly answer Ajay's question. Ajay's question is, if sigma activation were removed, we still have direction and weight. So Ajay, one of the reasons why this sigma plays a big role here is because if we remove this, it will cause an exploding gradients problem. The job of the sigma here is to make sure whatever we're sending to our short-term memory rate falls in a certain range. Because if you think about it, if we have a 60-word thing, this thing will keep on getting added over here, right? It will keep on getting added over here. I don't want to add something which will cause it to explode, right? I don't want one iteration to simply cause my long-term memory to explode. So to safeguard the values over here, I'm putting the sigmoid activation. Is that clear? Cool. Store means keep as a matrix or weight matrix. Bishwarup, by store, I mean keep as a vector, right? The CT, if you notice here, is a tensor. It's a tensor of some sort. So it will store it in the form of a tensor over here. So the size of this tensor will depend on the latent dimension, right? We decided it will be 300. So the tensor in which we're storing this memory is a vector. It's not a weight matrix, it's a vector. Okay, cool. So guys, are we clear on the input gate now? Is everyone with me so far? Are we clear on how this input gate is functioning? I have two-stage process. One stage is calculating my direction. Other stage is calculating importance. Overall, it's being added and sent to here. Okay. Now let's talk about the forget gate. If we have put some information, we have to make sure we are able to forget irrelevant information, right? So if we encounter things like off, the, to, from, all our stop words, right? For all our stop words, we should try and forget those things from our long-term memory. So that is why we will now focus on this forget operation. Okay. So now let us see this forget operation. Okay. So this is my forget operation. Let's see this. So now guys, for this discussion, I want you to imagine that this is non-zero. Okay. And this is also non-zero. It won't make sense. It won't feel intuitive unless we are discussing in that case, right? In the non-zero case. So let us now imagine that I'm getting some contextual information, long-term information from the previous iteration, and I'm getting some short-term information from this HT. Okay, so I have this CT which is long-term, HT which is short-term. I'm now going to do some operations so that I can use the current word to decide if I want to forget something from this. Okay, So how am I forgetting? To understand how we are forgetting, let us focus on this operation. Can you guys guess what this operation is? We have already seen this other places, right? What is this operation? What is this operation, guys? Element wise multiply, right? This is element wise multiply. Right, exactly. Element wise multiplication. So now I want you guys to imagine this. I have a 300 length vector which is capturing the direction. Okay, think of this as capturing the direction of some information that I have. Okay, let me take a small example. Instead of 300, we'll go to 3. So 0.3 minus 1 point, no, minus 0.2 and say 0.01, something like this. Okay. Now, I want this vector to forget something, right? So I have the input embedding over here. I have the hidden state over here. At this stage, I'm simply going to concatenate both of them. We've already seen this. This is nothing but a concatenation operation. So first, what was I putting? I was putting xt first. Okay. So first I'll have my xt, then I will have my ht minus 1. This is my concatenated vector. I'm going to take this vector now. Okay, so we are now basically focusing on this path. Okay, we're focusing on this path. So what I'm going to do is I'm going to take this vector. Okay, oops, sorry. Yeah, I'm going to take this vector. I'm going to multiply it by this wf. Okay, wf. The wf over here, guys, the f stands for forget. Okay, the f stands for forget. So I'm going to take this wf. I'm going to multiply it with this concatenated vector. Okay, and I'm going to add a bias term to it. This thing now I'm going to pass through a sigmoid operation. Okay, if I'm passing it through sigmoid, again, what is the range going to be? What is the range of these values going to be? Between what? 0 to 1, right? Clear. So now think of it this way. Let us say this operation gave us an output which looks like this: 0.03, 0.9 and 0.5. Okay, so think of this again as something which is deciding the relative importance of this direction. Okay, the relative importance of the entries in this direction. If I now do an element wise multiplication between these two, do you guys see that I'm asking it to forget whatever it has learned in the first entry? Do you guys observe this? I'm multiplying this with a very small number, right? I'm multiplying this with a very small number. So by doing this multiplication, I'm basically telling this long-term memory to forget whatever you have stored in this part. Yeah, whatever is stored in this part. This multiplication is going to say whatever you have remembered here, that is very important, keep it. And this part is telling it whatever you have stored is also quite important, but not as important as that other one. So that is the job of this forget gate. The job of this forget gate is to create a vector, a weight vector like this yellow one here, so that I can tell my long-term memory what to remember, what to forget. Okay, that's the basic idea here. So let me quickly address Arun's doubt over here. So basically sigmoid acts as a filter, but since we're applying it on the word embedding, it acts as a context filter. Perfect. Perfect, Arun. That intuition is perfectly captured in your statement. Love that. Okay. So that is exactly what we're doing here. The sigmoid is a filter. It is deciding among the word embedding that I have, which directions are important, which directions are not important for this word embedding. And accordingly, I'm updating my context here. So think of this context vector as a vector in that embedding space. If you start thinking of this context vector as a vector in that embedding space, Arun's statement will make a lot of sense to you. Okay, cool. So this completes the forget operation. Okay, so now we have seen how information is going into this long-term memory, how information is coming out of this long-term memory. Finally, let us now go and see what happens in the output operation. How am I going to now use my context memory, my long-term memory and my short-term memory to generate the output of this layer, right? Let's focus on that now. So now let's focus on the output operation, output gate. All right. So for this, again, I'll have to bring my image over here. Let's quickly bring this. Okay. And the path that we're interested in now is basically this one, whatever I'm going to highlight in yellow. So now what we're interested in is this path. We're only interested in this path. Okay. This is what we're interested in. Cool. So once again, at this point, we have our concatenated vector xt comma ht minus 1. This is our concatenated vector. When this concatenated vector reaches here, what we will have is WO. So WO, the O in the WO stands for output. So we take this WO matrix, we multiply it with this concatenated vector. Okay. We add a bias term associated with this output dense layer. Okay. This is what we're getting at this stage. Now notice that we're passing it through the sigmoid to get this OT over here, right? So OT now is equal to this term ka sigmoid. Oops, sorry. Okay, I'll have to write it. Let me write it. Sigmoid of WO times xt comma ht minus 1 plus BO, right? We're passing this through a sigmoid. So again, guys, quickly tell me, what is the range? This is also going to be like a weight vector, right? Sigmoid means weight vector, 0 to 1. Okay. So, Bishwarup, I'll come back to your question shortly. Just let me finish this. I don't want to break flow. So let me finish this for now. So when I reach this point, I have this OT, which is nothing but like a weight matrix with my current context. Okay. This is like the weight matrix from my current context. Now, this is where it gets interesting. Okay. The output that I'm giving here is HT. So let us now try and understand how we are getting HT from OT. Okay. So let's focus on that part now. Do you guys see the CT is coming from here? So the forget operation has already been applied. The input operation has already been applied. So now my context information, right? My context information, my long-term context information is ready to be used to generate my output. Okay. So the way you should read this diagram is, okay, the way you should read this diagram is CT is going here, forget operation is being applied here, and input operation is being applied here. Then it is flowing into this tanh. So this tanh operation you see here is being applied to the entire contextual information vector that I have. Okay. So the thing that I get over here after this tanh, right? The thing that I get here after this tanh is nothing but tanh of CT. Okay, this is tanh of CT. Okay, okay. Now, if you notice here, we are doing an element-wise multiplication between this OT and this tanh which is coming here, right? So, and whatever this output is exactly what I'm calling my HT. So my HT is nothing but an element-wise multiplication of this OT and this tanh of CT. So let us write that equation down. HT is tanh of CT element-wise multiplied by this OT. Okay. And this is how I finally generate the output of the LSTM. Cool. This is how we generate the output of the LSTM. And the same output without any change, is passed as the short-term memory of the next layer. Okay, this is what's interesting in LSTM. Okay, cool. Okay. One moment. So let me now. I see that there are some questions. Let me address them. First question is by Vishwarup. Let me address Vishwarup's question. How are WF, WI, WC different biases? No. They're different matrices. So this WF over here is the forget weight matrix. WI is the input weight matrix. WC is the context weight matrix and WO is the output weight matrix. Okay. Think of these as different matrices. The dimensions of each of these matrices have to be the same. Why do they have to be the same? Because of all these additions and multiplications we're doing, right? So the dimensions of these have to be the same, but they're all separate matrices. We will actually learn these matrices during our training. Okay. So Bishwarup, I hope that answers your question. Okay. Gradient flow makes them different weights. Yes, Vishwarup. Gradient flow will make them different weights. When we initialize also, they will start at different points, right? We usually initialize randomly. So just like in our feed-forward neural network, every weight matrix in our network was initialized differently. It will start at different values, and gradient flow will force them to make it different values also, right? So that's what. Okay. So Indradeep's question to me is, what is the loss in this LSTM unit? Indradeep will come to that. Just give me 2 minutes. For now, let's focus on this input-output relationship. Okay, cool. Let me take up Anil's question next. OT has both long and short-term component for this LSTM cell, right? Yes, Anil. Beautiful. See, it has the short-term component because of this HT-1, which we are working on, right? This HT-1 is the short-term. So let me mark this. This is actually a very nice observation. I want to highlight this. So this is the contribution from short term. Okay. And the long term contribution is coming from this CT, right? So this is the contribution from the long term. Okay. I understand that this is a bit confusing. Usually we say OT to represent output, right? But in this diagram, guys, OT is this intermediate state. Okay. The output of the LSTM is this hidden state that we are passing to the next one. In an LSTM, whatever hidden state we pass to the next one is the output also. Okay. This is something we have to remember. Okay. Anil's question is, didn't get you. CT has both long-term and short-term component for this LSTM cell, right? Yeah, CT is only the long-term. CT is calculated using the short-term, right? Didn't we discuss this? Our condition was, see, when we had this discussion, our input operation should allow things to go to long-term only from short-term, right? The only connection between this long-term and the rest of the world is through this short-term. So my CT, okay, so let's come back to the output gate. The final output that I have here is this HT. HT is equal to tan H of CT into OT. Now this OT is sigmoid of all this, right? So the final output that I'm getting, okay, is having contributions from short term as well and long term as well. This is what I mean, Anil. Does that answer your question? OT has only current info? Yes, OT has only current info. Correct. But OT is not the final output of my LSTM. Okay. Naveen says, in element-wise multiplication after OT, is it OT into tan H of CT or OT into tan H of CT minus 1? Naveen, it is OT into tan H of CT. CT. See, by the time you pass through the, see, look at it this way, okay, Naveen? By the time I cross the forget gate and by the time I cross the input gate, I already have something which is different from what came here, right? But if you notice, this is not affected till the next cell. This CT is not going to be affected till the next cell. So that is why what we are getting here is CT and not CT minus 1. Is that clear? Perfect. So this is CT only. Okay, cool. Anil, have I answered your question? I'm not sure if I have. Anil, you're right. OT has only current info. So does that answer your question? Is it okay if I proceed now? I want to now quickly go to the gradient last final discussion. Guys, it looks like today maybe I won't be able to discuss the implementation details because we're running out of time. In that case, what I will do is in the next class, we will keep. So guys, the implementation details of this is kind of important. Okay. So I want to discuss that in detail. If possible, I will try to cover that in the next class. Just warning you right away. For now, let us see through examples how these things are working. Okay. Let us see through examples how this is working. So to understand through examples, okay, how this is working, let us take a sentence. Let us see how it will pass through this. Let us see how it will pass through this. So my sentence is, I like to travel and visited Paris last year as a part of my business trip. Blah, 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 blah. He says, I could see the Eiffel Tower. Then he says, I took my family to on vacation to Cairo, where we saw some pyramids, right? So what I want you guys to focus on here is when we are reading the word Eiffel Tower, what the long-term information that we want a connection with is Paris. When we're reading pyramids, the long-term information that we want associated with is Cairo. Okay. So as we transition from this paragraph to this paragraph, okay, we want to forget the Paris wala thing and we want to now start remembering Cairo. Is the requirement clear here? As I'm reading this sentence, I want my network to associate Eiffel Tower with Paris, and I want my network to associate pyramids with Cairo. Okay. So through this example, we're going to see how these things are working. Okay. So, guys, with me so far? Are we ready to understand through this example, or should we pause? Okay. Okay. We're ready to understand. Okay. So now we're going to take this example and we're going to try and imagine how the network is going to, first of all, remember this Eiffel Tower Paris thing. That is number one. Then it has to forget Paris over here when we come to Cairo. And then when it sees pyramids, it has to build a connection between Cairo and pyramids. So if I had to write this as an operation at an operation level, there has to be an input operation when it comes to Eiffel Tower, right? There has to be an input operation at Eiffel Tower. There has to be a forget operation at Cairo, and there has to be an input operation at this pyramids. So let us now, through this example, see how this could happen. Okay. So I've taken this input gate. I have passed everything up till Paris over here. Okay. So now for this to encode Paris over here, what needs to happen is, first of all, the embedding vector of Paris has to pass almost as it is to this part. Okay. The embedding vector has to pass almost as it is to this part. I also want the weight to be high over here, right? I want the sigmoid to give me almost all ones over here, right? If the sigmoid is almost all ones here, if my IT is almost all ones here, then whatever embedding representation I had for Paris is now going to be encoded here. Do you guys agree? I want this to be ones. I want this to be close to the embedding vector. And once I add it to my previous one, I will have Paris in my long-term memory. This is how the input is happening at the Paris word. Cool. Now let us see what happens when we encounter Cairo. Okay. So the moment we encounter Cairo, I want to forget the relationship that I had with Paris. Okay. For that, what needs to happen? Cairo's embedding needs to go through here. It somehow needs to go and access only that part of my hidden state which is encoding locations, right? So this operation now has to make sure that it is going to that vector which is storing the location of words. It has to forget that. So it has to put a 0 wherever those things are encoded, right? It has to put a 0 there. Once the 0 gets multiplied with this Paris wala vector, it will now free up that memory. Okay, now the Paris association will be forgotten, and because of this other input gate that is going to come, we will encode Cairo over there. Okay, so that is how a forget operation followed by an input operation will remove the Paris association with Eiffel Tower, and it will store Cairo now. And finally, once we cross Cairo and okay, it's not there. Okay, so finally, once we cross Cairo and we come to that pyramids part, again, we need to have an input operation that goes there. The input operation has to take the information from my embedding for pyramids. It has to add it over there, right? So broadly speaking, this is how my LSTM is able to regulate what gets remembered in the long-term memory and what gets forgotten. Okay. The whole game is in these sigmoid vectors. Why are we putting sigmoid vectors there? Because these sigmoid vectors are what are adding as gates, right? Why am I calling them gates, guys? It's because I'm using these sigmoid outputs to adjust the importance of those entries. Okay. So this is why the LSTM architecture is quite effective. These gates are what control what goes into my long-term memory, what comes out of it, and whether stuff has to be forgotten or remembered. Like those kinds of things are taken care of by the actions of these gates. Okay. So hopefully now we have understood at a high level how our architecture is able to do these things. Okay. How our architecture is able to do these things. Cool. So let us quickly discuss vanishing and exploding gradient problem for this, and maybe quickly discuss the architecture of the GRU, and this code implementation part we will do next class. Okay. The code implementation I will take up next class. Cool. So let me quickly see Deepit's question first. But what if Eiffel Tower word comes after Cairo? The chances of that are happening are a little less, right, Deepit? Because generally when you're writing a paragraph, uh, it comes there. So 1 minute. So what if we have an article where it goes back to that after this connection? So then during training, my network will have to decide not to do this forget operation. Okay. In that case, right, Deepit, my network will learn not to forget this association when Cairo comes in. It will try to encode it in some other way, right? So during gradient descent, think of it as a problem which happens at gradient descent. If my task requires me not to forget something, it will change the W and the bias over here. The forget gate will be changed in a way that this Paris, ET connection is not forgotten when Cairo comes in. So that's the idea. It all depends on how our data set is set and everything. So that's how. Anil's question is typical max context length windows possible for LSTMs is. I don't know this offhand, but LSTMs, it depends on the size actually. So Anil, it will depend on the size you choose for your context information and this, right? So the capacity of your network is decided by what size you put here. I think some really good LSTMs are able to store quite a lot of contextual information. So the maximum content length will scale according to the size. I can't tell you what the absolute maximum is, but I can definitely tell you that if you increase this, your memory will increase, right? But I have not seen examples where it's able. So all the examples I have seen a text summarization where the input lengths are 100 words or so. I have not seen this applied to a large body of text. I will do one thing. I will try to look for a paper where they've used LSTMs for large document summarization. Maybe that will give us an idea. So maybe remind me next class. I will look into this. Right? Just please remind me next class. Okay. Cool. So guys, before we conclude, I just want to cover this part quickly. How this vanishing and exploding gradients problem is solved. Right? Okay. So how does the LSTM mitigate the vanishing and exploding gradients problem? So for a basic RNN, the problem was with this gradient term over here, right? The derivative of HT, the previous hidden, the derivative of the current hidden state with respect to the previous hidden state. This was causing problems. This was something which was very small. But now, if we look at the long-term information, right? If you look at the long-term memory information, we see that the derivative of this has three parts now. This is the contribution of the forget gate. This is the contribution of the input gate. This is the contribution with respect to the hidden state. So the output gate's contribution is coming here, right? So this is how we're avoiding the vanishing gradients problem. Because I'm getting contributions from so many things, it is very low probability that all three matrices will send it to zero. Okay. So we're basically reducing the chance that it will go towards zero through these things. But if you pay attention, each of these terms is something which is between 0 and 1. Why? Why are all the gradients here between 0 and 1? Can you guys quickly tell me? Because of the sigmoid. Because of the sigmoid. Perfect. So because of the sigmoid, each of these terms is between 0 and 1, but the sum of these terms is not necessarily between 0 and 1, right? It's very low probability that all of them will go to 0 at the same time, or all of them will go to 1 at the same time. So because of this, the vanishing gradients problem is eliminated. Okay. Exploding gradients problem won't come here because of the way we have selected our sigmoids, right? Because of the way we have selected our activations, we will never encounter uh, these problems. So to the best of my knowledge, nobody replaces these with other activations. Tanh sigmoid is what people usually go for. To the best of my knowledge, this is what they use generally. So yeah, I've not come across an architecture which uses a ReLU there. Okay, cool. So this is how we are mitigating this problem. So finally, let's take a look at what all is being learned, right? So we are finally learning the following matrices. We're learning one dense layer over here, which is the forget gates dense layer. We're learning one dense layer over here, which is the input gates dense layer. We're learning one dense layer over here, which is the context gate over here. And finally, we're learning one over here. So the forget gate has one dense layer, the output gate has one dense layer, and the input gate has two dense layers. So finally, the learnable parameters here are WF, WI, WC, WO. Also imagine that we have the biases there, okay? They've not written it over here, but remember that there are biases also. Let me just add it here directly. So B underscore F comes here. I'll have B underscore I and B underscore C over here. And finally, I'm going to have B underscore O over here. So these are our learned parameters. So this is what we're going to learn. Okay, that's all. Cool. So now let us discuss variants of this gated. Let us quickly discuss this GRU. It is a variant of the LSTM where I'm merging the operation of the short and the long term. Okay. So this is kind of a complicated architecture. If you wish, we can take a look at the details of this math in the next class. So it looks like if I take this, if I start this now, I'll take another half an hour to discuss this. Let's take this up in the next class. Okay. Let's take this up in the next class. Now, for now, what I want to show you guys quickly is the output. Okay. So all of this is the code which will get the whole job done. I just want to focus on the outputs for now. Okay. So if we take an LSTM and we train it on a data set, I simply want to give you a view of what the output looks like. So let's take a couple of examples. Okay. So actress Deepika Padukone has denied reports that she is portraying Amrita Pritam in an upcoming biopic on poet. Okay, I can't pronounce this. Ludhianvi. Ludhianvi. Okay, Ludhianvi. Oh, Ludhianvi. Okay, I think someone from Ludhiana. Okay, Ludhianvi, which is being produced by Sanjay Leela Bansali. Deepika has currently signed Vishal Bharadwaj's next production, where she will be taking up the role of a gangster Khan, who was popularly known as Sapna Didi. Okay, so I guess this is that Golio ki Ramlila film they're talking about. So the original summary is this. Deepika denies starring as Amrita in Bansali's film. And the summary that we're getting from our model is Deepika to play in biopic on Padmavati Row report. So, okay. Is context like in terms of meaning, are these the same? Yeah. Okay. So she is denying that she is going to Bansali's film, and this is saying that she's playing in Padmavati. Okay, okay. This is not great, meaningful. This is not very meaningful summary of this. In fact, it is changing the meaning to some extent. Yeah, yeah. Don't jump to conclusions. Don't jump to conclusions. Wait. Let's see. Right? Okay, let's read this one. An Etihad Airways pilot passes away on Wednesday while operating cargo flight from Abu Dhabi to Amsterdam after the captain became in the flight the first officer issued an emergency call and safely diverted the aircraft to Kuwait. The airline said in a statement that the pilot was pronounced dead after receiving medical treatment. The statement added, okay. Pilot dies on board Airways plane midair, right? Pilot flies to fly plane with emergency landing. Okay, yeah. The model isn't great here either. Okay, so this is kind of counterintuitive. We ended up with an example which is not that effective, but yeah, interesting. Bekar hai model. We don't say that to someone who builds models. Yeah, I mean, all models are wrong. You only want to care about how they perform approximately, right? So you build a model to be wrong, Meaningfully, it's not doing such a great job. So maybe what we can do is next time we can try and see why this is the case. It looks like our summarizer is sort of changing the meaning of stuff, right? So let's see. US man finds worth something lacks while eating dash dish. Man of US woman's body to pay. Wow. Okay. Okay. This is really bad actually. Okay. This is something which will need a little bit of investigation. But we could probably debug why this is happening based on the loss function that we used and how we carried out our training, right? So maybe although we're not getting great outputs, what's nice is whatever it's generating is approximately related to the context of this, right? So I will still feel happy by looking at this output. I will say that I have a model now which is able to generate some meaningful sentences. The meaning is not exactly the meaning of the document that it started with, but it does seem to be doing it is giving us something which is meaningful. This is not garbage, right? So it is forming meaningful sentences. I'll just be happy with that. And later on, we'll see how to improve on this, right? So let's take that as the conclusion from here. Okay. I also did not have a chance to discuss this Rouge scores. Rouge basically means recall-oriented understudy for gisting evaluation. To be very frank, this is basically an evaluation metric which uses precision and recall with respect to the summary and the predicted summary. So this is something we'll again discuss next class. We'll probably cover the implementation and the GRU ka math in the first half an hour of next class, and then we'll continue with our discussion. Okay, cool. So what I'm now going to do is I'm going to start the doubt session. Those of you who don't have any doubts can leave. The rest of you can stay back for the doubt session. Okay, cool. So let me first answer Sean's question. Some of the text in the third example has some problems like ASCII is coming up. Also, probably LSTMs not be able to retain context. It would be good just for 1 to 2 sentences. Okay, let's quickly see this. Third one, right? Third example. Third one. Okay, this one. An Etihad Airways pilot passes away. Pilot dies on board Airways plane mid-air. Pilot flyers to fly plane with emergency landing. Okay, yeah. Oh, not this one. Okay. Can you tell me which one? Like, just give me 1 or 2 words. I'll look for it. Uh, some text below. Okay, okay. Let me go. Okay, you're saying that the ASCII itself is not coming out properly. This stuff, right? Yeah. So I think these are dollar symbols. So I think Kerala Chief Minister Blah announced ex gratia of rupees. So I think this is the rupees symbol. So rupees 10 lakh makes sense here, right? So wherever we see this, right, this ACA kind of thing, wherever we see this, you can assume this to be the rupee symbol. So now, how I will read this original summary is Kerala CM announces rupees 10L. This L over here is supposed to be for lakh. So 10L ex gratia for cyclone Okhi victims. Startup CM, no. UP CM. Okay, so we have gone from Kerala to UP. So I will still feel happy that the word it replaced with is another state in India. Yeah, the predicted summary is funny, but like the conceptual at a conceptual level, it is forming sentences well, right? So I would be happy with that result actually. So UPCM announces rupees 5 lakhs for liquor shops in Bihar. Yeah, I totally agree. This is like really weird. But okay. Well, this is what we have. This is what we have. But let's see. So let's take the positive. Yeah, let's take the positives from this. The positives are that we're able to form meaningful sentences. Even if it's making a mistake, the mistake is conceptual, right? Kerala CM became UP CM. The fact that both of them mean states means that our contextual information storage is working well. It's just not working that well. Okay? It's not working that well, but it's working well. I'll take that away. Another thing is this entire sentence is quite meaningful. It's funny, but it's meaningful, right? So I will take that as a plus sign. I will still look at this as a good result as opposed to everything we have studied so far because till now we have not been able to get meaningful sentences, right? So I will still take this as a good thing. Okay, cool. All right, guys. So now let me quickly take the questions on the questions tab. Yeah. Of course, Sean, something is always better than nothing. So, guys, you have to put yourselves in a researcher's mindset, okay? It is almost certain that you're going to take time to get to an answer. It is almost certain that you will take time. Every time you're getting an output, right? It may seem depressing that you have not achieved your goal, but you can only succeed if when you're failing, you see what is the plus things, what is the minus things, and then you go and fix the minus things. That is how technology is built, right? Nothing gets done in one day. Okay. Anyone who tells you that I figured out BERT or transformer architecture in one day, they're lying to you. It's a process. So when it comes to research and when it comes to technological concepts, it's important to go step by step. It's important to understand the importance of each component in that big architecture and then move on, right? I'll still take this as a good thing. I'll still take this as a good thing. So yeah, something is always better than nothing, Sean. Something is always better than nothing. And it is up to you to find that something as a researcher. So that's what. Yeah, cool. Now let me quickly answer Sean's question. For out of vocabulary words, creating word vectors on the fly for words not there in our vocabulary, what all ways are there to achieve that? Any model or any ways to achieve that? Yeah. So Sean, I found this training strategy. Okay. Generally, when you have out of vocabulary words, right, you have to retrain your network. So you have to retrain your embedding layer of your network now. Okay. So essentially what you do is you take the old embedding vector, you add a new position for the out of vocabulary word over there, and then the output vector is again the original thing followed by 1 0. So you basically retrain your embedding layer to add that new word over there. So it's like I'm adding a new dimension to handle the word I have not seen before, right? So generally that is how it goes. The only strategy which I believe works is you have to retrain your network. How would that work at inference time? So at inference time, essentially, okay, so you're telling me inference time out of vocabulary, what do you do, right? Inference time out of vocabulary, what do you do? Wait, I'll have to look into this. I've not seen how people encounter this. So my current answer or my current belief is if at inference time you're seeing out of vocabulary words, you can't do anything. Just remove them from that whole thing and hope that it does a good enough job. So what I would do is I would remove that word from my input or output, basically, right? Does that make sense? So I will not keep that word itself over there. Or if you remember, a couple of classes back, we had said that we will keep an extra word which represents out of vocabulary word, right? So we can do that also. So we can put a placeholder word there which we have trained for, right? Out of vocabulary. Yeah. So at inference time, I will replace it with either a word which means out of vocabulary, or I will remove that word from my input. That is two ways to handle it. If I want to do it better, then I will have to retrain. If I am retraining it, then I will have to retrain specifically the embedding part of it. I have to now assure two things. My old embedding should not be affected. My new embedding should be there only for the new words, right? Those two things are there. Azhar's question to me. First, let me handle Sean's question, then I'll come to you, Azhar. So Sean, does that answer your question? So essentially, I would have to now. So I'll just summarize once more for my own peace of mind. I will retrain my embedding layer in a way that my old embeddings are not affected, and the new words that I'm seeing will form a new embedding. So it will be like I can do it this way. One creative way I can think of is you take the old embedding, you now train a network only on the new words that you're seeing, and you simply concatenate them, right? If you simply concatenate them, that representation will achieve both purposes. So I would have tried that if I was doing this. Cool. Now let me answer Azhar's question. Is it possible to do transfer learning in LSTM? Azhar, no, it's not. Transfer learning in LSTM is not possible because the only thing which is capturing things is this contextual information, right? Uh, Generally, it will not do so well if the document changes. So in a corpus, so remember our discussions about corpuses and words. TF-IDF for one corpus will be very different from TF-IDF for a different corpus, right? So the relative importance of words changes corpus to corpus. How transformers solve this problem is by using a computational mechanism known as attention. So once we see attention, once we understand that, we'll see why transfer learning works there and not here, right? So that's the answer. Sean, I will repeat my answer for you. So yeah, what was I saying? I can solve this. So my problem statement is this. I want to not affect the vector representation of my old words. I only want to change the vector representations for my new words. So I'm now going to create a vocabulary only out of the words which are new to this corpus. I'm going to train a word to vec for those words. And then the final word that I send over here, right, is going to be a concatenation of both of them. Okay, so it's like this. Now this WF matrix will work on this part, right? The old vocabulary. Now I'm going to create another dense layer to handle the concatenated part of that thing. So I will now go and add new weight vectors for the concatenated parts. I will add them over here and then I will pass it on. So that will ensure that whatever I have trained on before still works. And the only thing I'm training on is this out of vocabulary stuff. So that's how we do it. That's one way I can think of solving this problem. So yeah. And so again, Sean, I have not seen any paper do this. This is an answer I have come up with based on my experience. I will confirm by looking at other papers what they do in those cases, and I will get back to you. I actually found one article here while I was discussing this. I'll just pin it over here. See if this is helpful for you, Sean. Yeah, see if this one is helpful for you. So this guy has a strategy which I sort of liked. He was facing issues in the training part, but he's facing that only because his data set is not big enough. So you can follow that, and we can discuss this next class. Okay, cool. Arun, sorry for the long delay. We're finally coming to your question. And Hema, I believe you also had a question, right? If you wish, I could take that up now. So please let me know. Arun, I'll just go back and see the hidden state question, right? I'll just bring that question here now. So just give me 1 second, guys. Hmm. Okay, so let's see this. Is this the question, Arun? Cool. So over here, which of the following statements is correct about the hidden state? It is present in both MLP and RNN. We know this is false because MLP is it's not there. When we are passing the first input, the hidden states are all generally initialized according to HE initialization. So this is wrong because we don't generally initialize it randomly. It's done sometimes, but it is not that effective. A better strategy is to keep a fixed vector. when we are passing the first input to the hidden states, all are typically initialized to zeros. This is one of the acceptable strategies, okay? So it is technically correct. So if I were you, I would have marked this as correct because it's one of the acceptable strategies. But I have seen in papers people mentioning that a fixed uh, vector makes more sense there. Like it works better for them. This is the claim that I've seen in a paper. So honestly speaking, it is not wrong. The statement is not false. It's incomplete, but it's not false. So if I were you, I would have marked this. And activation functions are typically used in vanilla RNA standard. So this is also there. So I would mark this as correct. Okay. Okay. One suggestion: more detailed explanations in hint section would be better. Sure. I'll definitely take this up. So improve hint section is the feedback that I've gotten. I'll convey this to the team which handles the assessment questions. More detailed explanations. Okay. I think third option is wrong. Can you check? Third option is wrong. Oh, okay. Third option is wrong. No, when I mark these two, I'm getting the right answer, man. It's saying correct answer when I mark these two. Oh, okay. I'll just show you this. I'll just show you this. On my side, it's coming. Like I'll just show you this. See, when I say submit now, it gives me correct answer here. So at least on my interface, it's coming properly. Ah, okay, okay, okay. You got it wrong. Okay. Ah, okay. Cool, cool, cool. Yeah. Okay. So awesome. I'll just mark this as answered. And if anyone has any other doubts, guys, we can discuss it now. If not, we can discuss it offline, right? So I'll just wait for a couple of minutes in case anyone has any doubts. Otherwise, we will end our session here. Cool. I see no more questions. So I'll end the class here for today. Happy weekend, guys. Hope you have a nice weekend. I will see you again on Monday and we'll continue our discussion on this LSTMs on Monday. Cool. Good night.